It's my great pleasure to have Professor Gareth Roberts here today. So Gareth Roberts is a professor of statistics at Warwick and director of the Center for the Research in Statistical Methodology, and also a Turing Fellow at Alan Turing Institute. And among his many achievements, he is a fellow of the Royal Society, and he gave a Markov lecture in 2016. He received Wolfson Research Merit Award from Royal Society. He's a IMS. He also received IMS Medallion and Royal Statistical Society Guy Medal in silver and bronze, and also received a Rollo Davidson Prize. So he was previously, before Warwick, he was a lecturer at Nottingham and Cambridge, and also Lancaster, professor of statistics at Lancaster. So today he will discuss a stereographic Markov chain Monte Carlo, which is a new Markov chain Monte Carlo algorithm that has better mixing property than the previously known ones. So I feel incredibly fortunate to have Gareth here today. So without further ado, Gareth, the virtual floor is yours.
Thank you very much. Thank you very much for a very kind introduction, and thank you to everyone for coming to attend my seminar today. Yeah, so it's a great pleasure to present my work to the seminar today, and I'm going to start off with a bit of shameless advertising, just in case anybody is interested. Yes, this is what. So yeah, so a group of us, including Eric Moulin, Michael Jordan, Christian Robert, and I, were lucky enough to get an ERC Synergy grant for what I think is a very exciting project based on Bayesian algorithmic foundations for autonomous decision-making network agents. And it's something which we're currently recruiting. So if anybody is interested at all in positions, these positions we have probably would be PhD students, given the audience here today. But if people are interested in postdocs, then we have positions available either in Paris, Berkeley, or Warwick. And I'd be delighted to talk to you about much more specific details of that. We're just getting all of this set up at the moment, so now would be a good time to get in touch. Anyway, as Chang'an said, today I'm going to be talking about what I call stereographic Markov chain Monte Carlo algorithms. And part of the philosophy behind these algorithms has been something which I've been sort of striving at for many years in terms of trying to improve MCMC algorithms. One of the problems with trying to improve MCMC algorithms is that very often you make things worse. And you make things worse because actually to make things better, you need to know things about the target distribution, which you don't necessarily know. So I've been interested for a while in what I call no risk MCMC improvements, which basically are algorithms which essentially, if you get things right, can improve things massively. But if you get things wrong, actually, it doesn't actually make things too much worse. And stereographic MCMC is an example of a collection of algorithms for doing this. And they're really very simple ideas, which I'll present as we're going along. And so this work is very much in its infancy. We have a collection of theoretical results and some limited empirical experience with it, which I can share with you. But I'd be very kind of grateful of comments that people might have as we're going along. So this is joint work with Jun Yang, who's currently at the University of Oxford, but will shortly actually be leaving to take up a position in Copenhagen, and my colleague at Warwick, Krys Latuszynski. And this is a paper which we archived and submitted for publication something like a couple of months ago or something of that order. So you're welcome to read it and send comments on that. Okay, so this is things which I'm sure most, if not all of you know, but looking at MCMC algorithms, of course, one of the sort of perennial issues with MCMC is that transient phases can often be long and arbitrarily slow, and that can cause an issue in terms of sort of steady state estimation or estimation of expectations, as we want to do in Bayesian statistics. Now the other thing, of course, is that, you know, in the stationary phase, we have many techniques for assessing accuracy, effective sample size, looking at ACF functions, and methods such as looking at expected square jumping distance of algorithms. But the transient phase, we don't have so many tools for. And of course, transient phase is often very short, but it could also be arbitrarily long. But one thing that's often not noted is that for many of the kind of algorithms that we're interested in, the transient phase may be computationally more expensive to actually implement for various reasons. And one of the samplers which I'll be talking about today will be a good example of that, where in terms of Markov chain time, the transient phase may still be relatively short, but actually the computational cost of that transient phase may still be extremely large. So this is a situation that we have, and so of course we're always interested in situations where we can eliminate or remove or at least minimize the transient phase or minimize the cost of implementing that. So what are we going to do in this talk? We're really going to focus this on two very basic MCMC algorithms. The first one's the oldest one in the book, which is the Random Walk Metropolis algorithm, as a sort of straw man for all of this. And we're also going to look at something a little bit more modern, which is a continuous time algorithm, the bouncy particle sampler, which I'll give a little bit more detail on if anyone's not familiar with it. But to be honest, I could have looked at others and things like Mala and HMC and many other sort of your favorite MCMC algorithms could actually be implemented in a stereographic way. And the stereographic implementations are things which you know, you could do to sort of your favorite algorithm. So I'm essentially going to focus on these two, for which I think there's already interesting results. We're going to be interested in heavy tail target distributions, because obviously heavy tail target distributions is something that's of particular interest or particular concern for heavy tail distributions is the issues of the transient phase of algorithms. So that's going to be a particular concern of ours, and in Bayesian statistics, which is where most of the kind of applications that I'm interested in are, then heavy tail target distributions are the norm for many classes of problems. So I'm also interested in I'll give some results in this talk in high dimensional limits and to talk about how our algorithms behave as dimension goes to infinity. And of course, there are, especially the Random Walk Metropolis algorithm, that we do understand the sort of some of the limitations and how the curse of dimensionality can affect the Random Walk Metropolis algorithm. And we're going to just review that very briefly, just with view of introducing the stereographic versions of these, for which you know, a lot of these kind of issues about mixing and high dimensional behavior can be ameliorated. So we're going to introduce the stereographic projection sampler, which is called SPS, abbreviated SPS, and the stereographic bouncy particle sampler, which is the SBPS. So we'll introduce those two algorithms, which are essentially versions of the Random Walk Metropolis and the bouncy particle sampler implemented in a stereographic projection way. We're going to see some nice results about the behavior of these algorithms for heavy tail target distributions, and in particular, these algorithms have much more stable, robust properties in terms of things like uniform ergodicity. And secondly, and this is just for the bouncy, the Random Walk Metropolis algorithm, I will give some results about what happens in high dimensions, how the mixing time increases with dimension, and also how we can directly compare the behavior of the stereographic samplers with the random walk metropolis in Euclidean spaces, and hence kind of link back to what I said right at the beginning about this idea of getting samplers which are sort of no risk, in the sense that these algorithms are always at least as good as the random walk metropolis alternatives. Okay, right, so this is stuff I'm sure you've all seen before. The random walk metropolis, the good old-fashioned random walk metropolis algorithm, still a useful benchmark for comparing things with, and in fact still rather robust compared to many of the more sophisticated algorithms that people use. Although, you know, in virtually every application there are algorithms which are massively quicker that could be implemented. So how does it work? Basically, we choose a new state according to a normal perturbation with a variance h squared times the identity. I'm not looking at proposals which are not isotropic here, and these moves are accepted with the probability determined by the ratio of pi's. And of course, one of the things about this is that we have to tune h. So if we make h too small or we make h too large, then we can get the sort of mixing that we get in the first two plots here. This is an example on the left-hand side where the mixing is where we chose h to be too large. Here's a situation where we chose h to be too small, and this is a sort of optimized h. And of course, that's something that we can try and do. And so when I look at algorithms and compare them to random walk metropolis, I always like to compare them to, in some sense, the optimized random walk metropolis to be fair to the straw man. Okay. Of course, we do have the problem that mixing times can be, you know, quite slow. But I mean, actually, the dimensionality behavior of the random walk metropolis is not awful for many sort of reasonable classes of target distribution, which I won't go into in detail here. But one problem that we do have is that transient phases for random walk metropolis can be arbitrarily long. And in particular, for heavy tail target distributions, then these algorithms systematically fail to be even geometrically ergodic. So convergence is polynomial at best in many applications. Now, the second sort of straw man algorithm that we'll look at is something that's really rather new. The bouncy particle sampler, which is an idea which, like many of our ideas, originated in physics. And it's an example of a piecewise deterministic Markov process, which is, these are continuous time and piecewise smooth algorithms. Essentially what they do is they construct deterministic smooth dynamics until some abrupt change in direction according to some kind of hazard rate. And so these were originally introduced back in the 80s or even earlier than that in special cases. But there's a very nice paper in RSSB by Mark Davis, which introduced and gave some theoretical underpinning to these areas. What do these do? Essentially, they carry out some kind of deterministic dynamics, and at some hazard rate, lambda, they change direction. And so the generator of such a process is given by the equation here in the middle. And the recent development really is that within the last sort of 10 years or so, people have been interested in these as MCMC algorithms, as alternatives to algorithms such as Hamiltonian Monte Carlo and Mala algorithms, algorithms which use the derivative information about from the target distribution in a rather different way than, for instance, HMC. And the simplest example of such an algorithm is the bouncy particle sampler. And I'll introduce this in terms of a diagram really here. And what this does is essentially, it has a hazard rate. It essentially moves at constant velocity. So imagine moving along this particular straight line here, this arrow here. And what happens is it has a hazard rate of changing direction, which is dependent on how steep we're going downhill, which is essentially given by this inner product here between our velocity and minus the gradient of log pi. So that's a measure of how steep it is going downhill. And if we decide to change direction, then the canonical BPS algorithm is the algorithm essentially that says, well, when I change direction, what I shall do is I shall look at the contour, which I'm currently on, draw a tangent there, and then bounce perfectly with respect to that contour. Okay. Now, sort of very sort of easy kind of 2 or 3 line proof is that an invariant distribution for this is just the is pi, the invariant density, crossed with an independent distribution on velocity space, which is u. And so this is the invariant distribution, and it's the invariant distribution on this should be x comma v, not x dot v. One issue about this is that if you actually apply the canonical BPS, there's an issue about whether you have irreducibility, and it turns out rather alarmingly that even on something like a 2-dimensional isotropic Gaussian distribution, the canonical BPS is reducible, and it produces trajectories like this which fail to go inside a circle centered around the origin. But it turns out that you can make canonical BPS irreducible using a very simple and very flexible technique, which is to have an excess switching, which is essentially a technique which says that wherever you are, if I can have an additional excess switching rate, which I've denoted here by nu, which is a switching rate at which I just change direction in a way which doesn't depend on the target distribution. So if I do this, then it's relatively easy to show that such an algorithm is irreducible under rather general conditions. Okay, so this is what the BPS algorithm is, and hidden behind some of the results that I'll talk about later will be results about sort of optimizing things like the excess switching rate and things like that, which I won't particularly go into. Well, if anybody's interested, I can sort of say something about that at the end. So just to say something about the current state of play in terms of PDMPs, and it's kind of interesting. I mean, so this is a very, very flexible family of non-reversible continuous time MCMC algorithms. Okay, so and the non-reversibility can lead to many advantageous situations in terms of MCMC, and unlike the Random Walk Metropolis algorithm, the Metropolis algorithm in general, the theory has developed around these much more rapidly and before empirical experience. So actually, things like the high-dimensional properties of these kind of algorithms is understood much better now than actually sort of the empirical experience. And even though these algorithms have been used very, very effectively, particularly in various physics applications, the empirical experience is still very much lacking. And also the reason why I think they're not as popular as standard MCMC algorithms is, of course, that there isn't the software out there that allows people to implement these things. And continuous time algorithms are particularly complicated to implement, and so it's difficult for non-experts to pick these things up and use them. And I wanted to highlight one other issue, which is a sort of a disadvantage that's particularly an issue for this talk here, is that PDMPs are particularly affected by long burn-ins because their implementation needs to use things like Poisson thinning techniques, which tend to be expensive when you're in the tails of distributions. Not always, but they tend to be expensive if they're not sort of implemented in particularly efficient ways. And so therefore the issues about wanting to sort of reduce burning cost is particularly relevant in the context of PDMPs. Okay, so just to say that some of some of the things that we might want to have. So even some of the very basic properties of MCMC algorithm for heavy tail target distributions, which I'm particularly interested in, is that you don't even have basic properties very often. So things like Markov chain central limit theorems for all suitable L2 functions is something that you generally don't have for MCMC algorithms for heavy tail targets. And things like geometric ergodicity often fails. For instance, the Random Walk Metropolis, Hamiltonian MCMC methods, Mallah methods, or most of the PDMP methods that people implement fail to even be geometrically ergodic, let alone the strong or uniform ergodicity. So many of our MCMC algorithms that are used in statistics in particular don't really have as much theoretical support as we'd like to have. So we'd like to be able to construct algorithms that can sort of retain these kind of properties, in particular geometric ergodicity and the existence of central limit theorems as generally as possible and as robustly as possible. But we'd like to do this in using mechanisms that doesn't make things worse. And you know, many people have tried, and there are lots of very good suggestions out there for improving algorithms and for making them geometrically ergodic. But they often have the properties that they can make things worse if you don't implement them in the right way. Yeah, and so this is just illustrations of this Random Walk Metropolis. This is a kind of classic Random Walk Metropolis result. And if you go back to Kerry Mengerson and Richard Tweedy's work in 1996, shows that Random Walk Metropolis is not even geometrically ergodic for any heavy tail target distribution. And you can generalize that result in all sorts of ways, and it has been generalized in all sorts of ways. But it's not it's a worrying result for many statistical applications where we have heavy tail distribution, heavy tail marginal distributions in particular. It turns out that the PDMPs don't do any better, and the bouncy particle sampler with unit speed at least is not geometrically ergodic for any heavy tail target distribution. These algorithms are just not well suited when there's a lot of mass out there in the tails. And this is in the thesis of my student Georgios Vazdegis, who also proposes some ways to improve that by speeding up BPS in the tails. Okay, so this is something that we'd like to improve on if we possibly can. Okay, so I just wanted to note some sort of interesting properties about high-dimensional random walk metropolis algorithms and what Gaussian distributions even look like in high dimensions. And these factors, of course, are very well known. But every time I talk about them, I surprise myself in the sense that it's very counterintuitive. So we get this very intriguing phenomenon that if I have a d-dimensional normal distribution pi, then essentially all the mass is concentrated on a sphere of radius d to the half. Okay, so it's not really, the mass is not really concentrated anywhere near the mode. All the mass is really concentrated on a sphere of radius d to the half. And it really is an undergraduate exercise to prove that this is the case. But it then makes you think about, well, so if I want to actually simulate from something like a nice unimodal density, like a d-dimensional normal, you know, so what sort of algorithms really are the right sort of algorithms to be using in this context? But it also tells us if actually constructing an algorithm like a random walk metropolis algorithm or any kind of algorithm, then the mixing time of an algorithm is going to be no smaller than how long it takes us to actually arrive at this sphere of radius d to the half. Okay, so essentially that's going to be somehow a lower bound on convergence. It doesn't guarantee that we're actually converged, but essentially that's something that we can use to sort of show how limited sort of standard techniques might be. And so if I look at random walk metropolis in high dimensions, then of course only one direction may be pushing in the right direction towards this shell of radius d to the half, and all the other d-1 directions are actually going in the wrong direction. So we're doing an awful lot of work without actually doing anything kind of sensible for the random walk metropolis algorithm. And so if I do this at a stationary optimal strategy, which is also more or less optimal in the tails for random walk metropolis, of taking an algorithm that accepts about a quarter of its moves and has a step size which scales like 1 over d to the half, then it can still take order d to converge, and that's the best case scenario. What about the bouncy particle sampler? Well, the bouncy particle sampler has this issue which I alluded to earlier, that it can have reducibility properties unless you do use refresh. But if you do refreshment, then actually it can have properties which actually converge also at order d. And I'm not going to go into this in great detail, but you have to get the right amount of refresh, and if you do that, then you can get mixing, which is kind of comparable, and actually even sometimes slightly better than random walk metropolis. Of course, it's a continuous time algorithm, and what we really need to look at is the implementation time. Okay, so these algorithms can be okay, but they're not sort of outstanding. So we're interested now in trying to improve these, and stereographic projection is the mechanism that we're going to use. And many of you will have seen stereographic projection in some context or other. It's a very simple idea, is essentially to place a sphere of a particular radius, which we will choose as an algorithm parameter, put that sphere on top of the r to the d, just sort of place it on top, and then the North Pole here is going to have a special status, and essentially what I'm going to do is I'm going to project every point on r to the d. For instance, at this point that I'm highlighting here, I'll project it onto a point on the sphere, which will be around here, by a straight line which joins this point and the North Pole of the sphere. Okay, so there are very simple straightforward formulae for how this works and where the point on the sphere is. And essentially, the algorithms that I'm going to look at essentially are just carrying out the simple random walk metropolis mechanism or the bouncy particle sampler mechanism on the sphere rather than on r to the d. So that's basically all we're doing in these algorithms, but with some surprising effects. As you'll see from this, the North Pole has a special status, right? So the North Pole is actually going to be the projection of infinity in every direction. So the behavior at North Pole the North Pole of this sampler will turn out to be key to the behavior of the entire algorithm. If a behavior at the North Pole is reasonable in some appropriate sense, then it will give some nice properties to the algorithm. Okay, and the other thing to notice is that, of course, there are various parameters here. We can actually choose to locate this sphere at any place, and it sort of seems kind of a natural that we might a starting point, at least, that we might actually put the sphere, we might actually place it somewhere around the mode of its distribution, or somewhere around the middle of a distribution in some sense. And we'll come back to that later. So there are basically two things that we can choose for the stereographic projection before we even start to construct algorithms. One is the dimension, is the diameter of the sphere, and the second thing is the location of the center of the sphere, where it's actually touching r to the d. There are other things, of course, we can do. We can actually produce ellipsoids instead of spheres and things of this kind, but I'm not going to go into that in any detail here. Okay, so how does the stereographic projection sampler work? Well, essentially, it works according to the diagram here. So don't look too much at the equations here, because all the equations are doing is the following. Well, essentially, what we're doing is, if we're currently at this red point, this small red point here, which I'm ringing, I'm going to basically draw the tangent plane at this point, and then I'm actually going to make a move by moving along that tangent point, maybe to this point here, up here. And from this point up here, I will stereographically project, I will project this point back onto the sphere to this next red point here. That can all be done very, very cheaply. And because of the constant curvature that we have on the sphere, it turns out that there's no sort of Jacobians that we need to calculate that would be costly and might actually slow things down in terms of implementation. So this is it's actually a very nice. So essentially in blue, I've noted there the reverse move, which basically has the same density in terms of the proposal, and therefore I still get a nice accept reject, and so the accept reject ratio that I have for this algorithm is just given by the formula at the bottom, 1 min the ratio of the pi's, and then there's a term which involves the projection onto the sphere, which is just these r squared plus mod x squared all to the power d. So this is something that can be implemented very easily, and it can be thought of as just an alternative to the Euclidean-based random walk metropolis. So think a little bit about its properties. When we're near the North Pole, this is going to make a move which may be still relatively small on the sphere, but is actually going to make a massive move on the original state space. So we might be very interested in that, because essentially that's allowing us to move around much more quickly when we're in the tails. But maybe that can actually make things worse, because we might be in a situation where we get stuck in the tails because we're trying to make moves which are too big. And we'll see situations where we can control that possibility in a bit. I have so I don't want you to read this slide. This is what we do for the bouncy particle sampler. I'm just going to tell you in words what this really does. The algorithm, the pseudocode here is really just here to show you that the algorithm's not complicated. But essentially what we're doing is we are carrying out great circle movements on the hypersphere, and we're going to then disturb those great circle movements according to a hazard rate, and then we're going to change direction to move along a different great circle route. What does such an algorithm look like if we project it back onto Euclidean space? Well, I've got some examples here. So on the left-hand side here is the canonical SBPS, that's the canonical stereographic bouncy particle sampler, which has no additional refresh. And you see that also there's still a sort of area in the middle here that the sampler fails to actually reach. But if we actually have additional excess refresh, then this becomes irreducible, and it's something that we can actually prove. But you see that on the Euclidean space, the great circle routes that we chose on the sphere turn out to be these kind of curved sections. Some of them are more curved than others, depending on how far we're in the tails and various other things. So these are the kind of trajectories that we basically follow. Okay, so these are just illustrating this on a simple two-dimensional sampler. But what do these algorithms actually look like? Well, so we, as I alluded to earlier, the sort of crucially here, the North Pole is going to be very important. So what actually how does the algorithm actually behave near the North Pole? Well, it turns out that there's a sort of nice property, and all of my statements here are translated back onto the Euclidean density, so we don't need to think about, I mean, but essentially what I'm multiplying, so pi is Euclidean density here, and the r squared plus x squared to the d is essentially the Jacobian that we get by translating that onto the sphere. And essentially all I need is for this quantity here to be bounded near the North Pole for the algorithm to be uniformly ergodic. And essentially that means that the tails of a distribution are no heavier than a multivariate student T distribution with d degrees of freedom. Okay. And that is essentially a best possible result, in the sense that if you have a situation where this quantity here is unbounded near the North Pole, then it's easy to show that the algorithm, the stereographic bouncy particle sample, stereographic projection sample of the random walk on the sphere is actually not even geometrically ergodic. So this algorithm can fail, and it fails essentially. It fails to be geometrically ergodic in situations where the transform density explodes at the North Pole, which is sort of what you'd expect from sort of general MCMC results when you have poles for where the density goes to infinity at particular locations. But the good news is that when you don't have tails which are that heavy, then the algorithm is just uniformly ergodic, and in particular, it can get away from infinity. It can get away from the North Pole or infinity very easily, and in fact, you have an entrance boundary for the behavior of the algorithm from infinity, and everything is computationally stable. Okay, so that's nice. Now, for the stereographic bouncy particle sampler, the results are somewhat more delicate, and the result that we have is actually we think sort of almost, but not quite sort of best possible. So we have a result that essentially says that the bouncy particle sampler can be uniformly ergodic, essentially under slightly weaker conditions than for the from the random walk version. Essentially translating it onto this multivariate student T distribution, it's when the degrees of freedom are bigger than or equal to D minus a half. So essentially we can have slightly heavier tail distributions. So we don't think that this is best possible, but it's the best that we can actually do. And in the sort of more heavier tail versions of this, some quite interesting things happen. So in particular, you can have situations where the density of the transform density on the sphere is actually infinite at the North Pole, and we can have Markov chains which are non-Harris. So we can have Markov chains which in theory are well behaved, but actually are not Harris recurrent. So if you have a trajectory which starts off aiming for the North Pole, then it has a positive probability of getting stuck at the North Pole. So you can get some sort of strange kind of behaviors, which obviously in practice you probably wouldn't see, except that they would show themselves up in non-robust empirical properties of the algorithm when we start near the North Pole or on a trajectory that's going to near the North Pole. Okay, so there are some interesting kind of issues there, but essentially the theoretical results are slightly stronger, even though there's sort of caveats in terms of how easy it would be to implement this in the extremely heavy tail case. And so one of the sort of the motivations behind putting everything on the sphere is this amazing property properties that we have for algorithms on spheres, or just stochastic processes on spheres that basically can move around very quickly. And if we look at sort of what happens in a large dimensional hypersphere, then sort of almost all the mass, as we said before, is basically on the hypersurface and is on this sphere, hypersphere of radius d to the half, and virtually all of that mass itself actually lives at the equator. So the algorithm essentially wants to reach the equator as quickly as possible. And one of the interesting things about if I construct Brownian motion on the surface of a hypersphere, then it gets faster and faster and faster, because essentially to reach the equator, it has more and more dimensions to actually allow yourself to reach there. So there is this weird property of the blessing of dimensionality that Brownian motion has on the hypersphere, which is something that we would like to mimic as far as possible using algorithms. Of course, we won't be able to achieve this kind of blessing of dimensionality property, but if we can use that as an ideal, maybe it can actually improve our algorithms. Okay, how's time going? Yeah, maybe I need to speed up a little bit. Okay, so I'll skip that and I'll just show you very quickly some plots here. So what can happen? So basically, you can have this property that the stereographic projection sampler can be arbitrarily fast. So here's a situation where stereographic projection sampler for a spherically symmetric target density can have essentially almost IID mixing, whereas kind of optimized random walk metropolis in Euclidean spaces can be essentially arbitrarily slow with arbitrarily long burn-in. Okay, so this is a sort of an ideal situation, and if you have something that's approximately spherically symmetric, then you can get things which look a little bit like this. But of course, in the real world, that may be very difficult to achieve. Another thing is that in order to actually achieve this, to get these incredibly kind of fast mixing properties, it turns out that we need to because of this property of the hypersphere, that if I'd run Brownian motion on the surface of this hypersphere, then it wants to rush to the equator as rapidly as possible. So in order for that to be the case, I essentially need, in order to have these very rapidly mixing stereographic projection samplers, I need most of the mass to be located around the equator. And to do that, I basically need to have the right radius for my hypersphere. And it turns out that if I have kind of unit variances in every dimension, what I need to have is for the radius of my sphere to be equal to d to the half. And it turns out that if I don't have the right radius, then the algorithm will get worse. It'll deteriorate either for the radius bigger than d to the half, or even for d less than half. And this is basically showing how this can be the case. This is showing when the radius is slightly smaller than d to the half, how the efficiency efficiency can decrease with dimension really quite rapidly. As you can actually see if you actually look at the scale on the y-axis. So the stereographic projection sampler can actually have this incredibly rapid convergence, but it can be much slower if we get the radius of the sphere wrong. But this is all sort of not very realistic, because in the real world situation, we won't know this. So the worst case scenario is it will be what will actually happen. The worst case scenario is that we'll get the radius of the sphere wrong, and we'll basically put the location of the sphere in completely the wrong place. And if that happens, then the target distribution will essentially concentrate on some small island on the hypersphere. And if we concentrate on a small island of the hypersphere, then the effective support of the distribution will look essentially be concentrated on an area which have very little curvature. And essentially then what will happen is, if I optimize whatever algorithm I'm doing, that algorithm will behave like an algorithm on Euclidean space. So essentially what's happening here is that you don't lose anything. Even if you completely misspecify both the radius of the hypersphere and also the location of the hypersphere, then I'm basically going to be no worse than the Euclidean alternative. Can we somehow quantify that? And it turns out, so we have some results on this, and I will sort of finish off by talking a little bit about these. So we have some results about optimal scaling in an idealized case, right? So if I look at the stereographic projection sampler, which is the random walk version here, if I look at target distributions which have a product form of this kind, right? So very, very idealized, dialyzed family, but ones for which I can make analytic progress, in particular as the dimension goes to infinity. And I'm going to standardize these such that the second moment of f is equal to 1. Okay. then it turns out that we can get something which is, if I look at the expected square jumping distance, which is like the quadratic variation of a limiting diffusion that you might have here for each component, then that expected square jumping distance is approximately the quantity here, 1.3 divided by this quantity on the bottom, which probably doesn't mean anything to you, but if you compare it to the Random Walk Metropolis algorithm on the Euclidean space, then the ratio of this maximum expected square jumping distance of the algorithms, which is proportional to the effective sample size, is given by this ratio here, right? Okay, because we get the top here is the quantity that we get for Random Walk Metropolis on Euclidean space, and the bottom is what we get in this kind of curved space on the hypersphere. And so this quantity, of course, is always bigger than or equal to 1, and it quantifies how much better we are than Random Walk Metropolis. And for a very, very rough density here, where the where the expected value of log f prime squared is actually very large, then this will be very close to, this is going to be very close to 1 and be very little advantage here. And in case you're sort of puzzled about this, for any density for which the expected value of x squared is equal to 1, it's true that this quantity expected value of log f prime squared is bigger than or equal to 1, with equality if and only if we have a Gaussian target. So if you have a Gaussian target, then in principle you can get infinite advantage, or you can get arbitrarily large advantage, at least by applying the stereographic version of the sampler. Okay, and that's the case where you have a completely isotropic target density, which is obviously very artificial, but it describes, you know, a situation in which you can get arbitrarily big advantage. So I want to, so maybe I'll kind of skip over this. I'm just going to give a slightly more general version of this. If I will go back to the previous slide, and we have this ratio for the advantage that we have relative to Random Walk Metropolis algorithm, and we can express that advantage in slightly perhaps clearer ways, at least in terms of our mathematical understanding. So I'll just go forward to express the following statement. So the gain, the red line there, is the gain that we have over Random Walk Metropolis in a sort of general case. And the gain is 1 over 1 minus the product of 3 terms A, B, and C. Okay, and here we're in a situation where A, B, and C are all quantities which are less than or equal to 1. Okay, and each of them, if they're close to 0, can mean that the gain is basically negligible. But all of them could in principle be quite close to 1. So if I look at A, it's the quantity that we looked at before, which is a measure of how close we are to Gaussianity. Okay, in some sense, because when we have Gaussianity, we have 1. Okay, but it could be arbitrarily small. B is essentially a measure of how well we positioned our hypersphere. So if mu, which is basically the mean of this distribution, is equal to 0, that's essentially saying that I'm positioning the hypersphere exactly at the mean of the target distribution, then B will actually equal 1. Okay, and then there'll be no cost due to the misspecification of the mean. And C is this measure of basically, a cost due to, did I get the radius of the sphere right? Okay, and this C also is a quantity which is maximized at lambda equal 1, and that will essentially mean that the radius is equal to the square root of D, which is the optimal case, and that is the case. And this also tells you how much you will lose out when you actually misspecify the optimal, what you misspecified the radius of the sphere that you're actually going to be using. So you can sort of see from this a measure of how we're going to lose efficiency due to these 3 factors, and that efficiency gain could be arbitrarily close to 1, but also could be arbitrarily small. Okay, I think I probably talked enough, and so I'm just going to we have some simulations for showing how the SPPS can work extremely well and can outperform the Euclidean version of the algorithm by kind of quite large amounts. In the examples we showed, basically it was the advantage was a factor of e to the 4, but the advantage can be arbitrarily larger than that too. And the advantage, importantly, is kind of uniformly the case, and the implementational costs are essentially comparable for the two algorithms. So in summary, what have we done here? Something very simple. So all we've done is we've mapped R to the D to the hypersphere, and we constructed our favorite algorithms on the hypersphere and essentially use those instead. So we've looked at the stereographic projection sampler and the stereographic bouncy particle sampler. Computationally, in all the cases that we looked at, there's essentially very little additional cost. There could be some additional cost in situations where the cost of doing calculations for pi are very, very inexpensive, so that the projection itself becomes relatively expensive, but that would be extremely rare, I think. And our main results, well, we have sort of theoretical results for both algorithms to do with uniform ergodicity for heavy tail target distributions, which is, I think, is a useful thing, and many things follow from uniform ergodicity, such as central limit theorems and things of that kind. We have mixing time results, at least in sort of isotropic target densities and sort of dimension-free mixing, which means that you can get, at least in these idealized situations, which are not very realistic, you can get sort of massive speed up using these algorithms. They're not so realistic, but actually the perhaps more realistic and perhaps more useful is the fact that we get these expected square jumping distance advantages, which kind of seem to hold in general, and we can actually prove results for product IID targets for optimally scaled SPS algorithms, and comparing that to optimally scaled Random Walk Metropolis algorithms. And something which I haven't emphasized on there, I think, is this kind of no risk strategy, which I think is one of the appealing properties that we'd like to sort of promote for these algorithms. We're doing lots of things at the moment. We're changing shapes of spheres and locations of spheres and radii of spheres and things of this kind. Looking at adaptive versions of these algorithms, this algorithm is particularly well suited to adaptation. So the adaptation is, I think, an important sort of aspect of this. We've been looking at sort of adaptive MCMC, formal adaptive MCMC versions of this. We've also been using sort of gradient-based algorithms and implementing within this context, and there's sort of interesting kind of ways in which you might do that, and the sort of obvious ways of using gradients on the tangent spaces are not necessarily the best way of doing it. So we've been using locally balanced proposals, such as those in the sort of recent work by Vogring, Livingston, and Zanella. There are also lots of sort of kind of cool things that you can try out, and we've been trying out a little bit. Having more than one sphere, ways of trying to sort of deal with multimodality, and doing this in sort of kind of interesting ways, when sort of in a way, and also that would link also to the adaptive kind of work that we've been doing. Okay, so I think I'll stop there and pause for questions. Thank you.
Yeah, thank you very much for a wonderful talk. Please join me thanking Gareth. Yeah, I mean, does anyone have a question? yeah, so if there's not, I have a question. So, like, if I understood correctly, when the tails are very heavy, the problem is that on the sphere, the measure is concentrated on the pole, and so I was wondering, like you mentioned at the end, like using different shape than spheres. So and also at the beginning using ellipsoid and so forth. So I would imagine that if you make the curvature around the pole smaller than the other parts, it may alleviate the problem a little bit and allow you to deal with heavier tails. Is it something that you're trying with different shapes, or?
Yeah, that's a great question. And so the one reason why we've been reluctant to move away from the sphere situation is that if I can just go back to one of my earlier slides. Oops, how does this work? I'll do this very quickly here. There's a quick way of doing this. Oh yes, there's this one here. Is this nice property that essentially when the curvature is constant, this move is automatically reversible. It actually has mixing advantages as well. But it has, in particular, it has computational advantage. There is no sort of Jacobian associated with the curvature of the sphere here. So we've been reluctant to move that, but you're absolutely correct. I mean, so the issue really is when you have the North Pole. It's not that the measure concentrates at the North Pole, but the density can actually be degenerate. So the density can actually go to infinity at the North Pole, and that's the problem. And of course, you could alleviate that if you somehow had a spike at the North Pole, and that could make things better. Whether that could be sort of implemented in a sensible way is a really good question. We haven't really particularly focused on that, but it's a very interesting question. You'd need something in order to improve the theoretical results. You'd need to have something which is not smooth. So it couldn't be a manifold this smooth. So it wouldn't be enough to have a sort of blip at the North Pole that was still smooth. You'd actually have to have something that's non-smooth, which is perhaps not differentiable at a point. And that might be quite difficult to do in a robust way, but it may not be impossible. So it's an interesting thought.
I see. Thank you very much. Does anyone else have more questions?
So maybe if I could ask a question. So you also mentioned that this procedure does not really depend on the base Markov chain that you're using. You could use any of the HMC or Mala or any of the other techniques to work on the sphere, or? So
you'd have to work out how to implement it on the sphere, and there are different ways. We are currently working on a Mala implementation, which is using the I mentioned it at the end of the slide. Some work by Jure Vogrink, Sam Livingston, and Giacomo Zanella. So we have a Mala implementation, and I think we could do a similar HMC kind of implementation. But yes, so yeah, I think in principle you could do that for your favorite algorithm.
So the challenge being just to particular the rejection step that you had.
Yes, obviously, yes, exactly, yeah. I mean, so the nice property. I mean, so obviously with HMC, there may be some. So we haven't worked on HMC yet, but we have a working implementation of the Mala thing, but it doesn't turn out to be exactly the same as a Mala algorithm on the Euclidean space. You could implement a Mala algorithm on the Euclidean space on the tangent of the sphere and then project down again. But for various reasons, that has kind of additional kind of computational costs. So we haven't done that. So yeah, but you can do, but there are lots of other algorithms that you could do. You could do component-wise updating things. You could do Gibbs sampling type updating things. So there are lots of things that you could do in principle.
Great, thanks.
All right. Anyone else? All right. So if not, let's thank Gareth again. Thank you so much.